reliable. I changed it at the last minute and forgot the L. Subtitle. The thing is a little smaller than I thought. The subtitle, in which Google thinks everybody is lazy. Hi, I'm Andres. You could call me Andres with the Estonian if you want. I mention this because I have 3 names, which is very common in the States. It doesn't happen here. Andres, Jaan, Tack. We just say Tack with a normal, straight Swedish, English-ish accent. I am not Andres. I am not Spanish. I am not Anders. I am not Swedish. Andres is how I teach other people how to pronounce my name, because that's closer than their versions. Andy is what my uncle calls me, but I prefer Andres. That would be just fine. I'm from Chicago, as we mentioned before. And I introduced this, I promised you in the title slide, a cloud computing talk, what my background is. And I still will cling to this. My academic background is in systems. So this means operating systems, distributed systems, storage systems, all of this sort of thing. I did this particularly at the University of Wisconsin-Madison. Right now, I live here for 3 years working at Skype. If you'd like to ask me about that, I would love to talk to you about that. This talk isn't really about what Skype does. It's more about the general discussion that's been going on in the community. But it does affect what we do, and it motivates my team in particular. So ask me afterwards, and I'll happily talk through that with you all. So, little overview of the buzzwords that I'm going to cover in this talk. The things that I deal with particularly are latency-sensitive interactive apps. I don't do a whole lot of batch systems, so long queries that take several minutes to come back, I don't have time for that. I probably have time for that, but I don't do them. I do a lot of cloud stuff lately. Azure, you can imagine, is a big theme within Microsoft. So it turns out the cloud is all about storage, and this talk is going to talk a lot about storage and the options that you have for making storage happen. The cloud, and generally pretty much anything that we do now, is going to be distributed, so that's going to come up. How many of you guys have heard of the CAP theorem? 6 or 7, that's good. You'll have to teach the people around you before I get there. I ask about this because the people who are into the CAP theorem have probably started making fun of your friends who prefer relational databases. We have to stop doing this as a community because it's misguided. And that's kind of what this talk is about. There's a tension right now between those that like to talk about the CAP theorem and those that like SQL and relational databases. So, to motivate all this, let's make another Twitter. Why? Because the world needs more. And it's a good example for what we're going to do. So probably, as we're all excellent developers, we'll pick a stack something like this. Starting from Apache, going down through PHP several versions ago, and finishing with MySQL, which will sudo apt-get install and close our eyes and hope that it all works out just fine. Technology doesn't actually matter, right? Probably if we're making our Twitter app, it's not going to be very popular for the start. No one is going to use our Twitter. So actually, all of this, the blue square, I forgot to label it, is supposed to be your computer at home in your basement. That's going to be just fine. Any data storage will do, sudo apt-get install, MySQL. You could even use flat files. It doesn't really matter. The only really big thing about this is that if the computer crashes and we want our grandmother to access our version of Twitter, we'll probably have to restart it and have some assurance that it continues working. But in general, if it's broken, it's probably our fault. I mentioned that data storage. If we reboot, it has to come back. This is pretty much, when you're in one computer, the only thing that we care about. Is that if things go crashing, we don't have to pick apart the binary file and figure out which bytes got left out, trim this off there, truncate that, and whatever else. We'd love a storage system, and MySQL will do this, Postgres will do this. Pretty much any SQL system will do this out of the box. That recovers from hard disk failures and hard operating system crashes. Which, I've said it several times, probably means SQL. Good old SQL. We've been learning to do this since we learned Rails in 9th grade. It's great. And I'm going to convince you that it's even more great. Now, the people that have seen this is a picture of the people that have seen the CAP theorem, being very skeptical. And it's actually true. SQL isn't that great. Relational databases are the things that are great. Why? We'll talk about this. One of the reasons that they're great is because they're old. The relational database came out very shortly after databases in general came out. So 1969, someone came up with this idea of organizing a system in a way that is mathematically addressable. So you can query the system arbitrarily. There's a system of indexes that arose from that and all of this. His name was Edgar Codd. 1 year after that, SQL came out. And where Codd did this beautiful mathematical thing that in theory should be extensible and should lay into all of the theory and contribute to algorithmic growth, SQL ignored all of that, did something that doesn't really scale very well, and everyone kind of made their own version of it. Postgres has their own, MySQL has their own, Oracle has their own. And it's considered one of the great failures of a standard, actually, in that it is not standard. There's parts of the standard that if you try to implement them, you will be sued for infringing upon someone else's intellectual property. Failed. But all of this got very popular, and it was followed by 30 years of constant improvement. This became a very big deal because the information age happened and everything had to be stored somewhere. So everyone really worked on this very hard. We got column-wise stores, which made certain queries really fast. We got B trees and B plus trees. Right now we take them for granted. These indexes that we use all the time, they didn't exist all the time. Someone made them. Two-phase commit meant that we could do the constant bank transfer problem. By the way, I have a feature request for TransferWise. I would like to transfer back from US dollars. Please make that happen.
Support the TransferWise code will accommodate your wish.
Yes. Right ahead logging, dynamic two-phase commit. Very, very smart guys have been doing this, and they've been doing it, like I said, for 30 years. There is a ton of research that went into making these things work for everybody. Absolutely every edge case, every professor needs his special case. And they even solve replication. This is kind of the regular shape of what you do when you have a SQL-based relational database. How you make sure that if one machine is exploded, that the data isn't gone with it. You make it several machines. There's a master machine that accepts all the writes and distributes it to the slaves, and the slaves eventually let that information out to people who are just reading it. And this helps maintain some consistency, which we'll talk about a lot. And I'm going to beat this dead horse a little bit further. Relational databases are really fast. The numbers are probably too small. The top number over here is an Oracle database cluster that has demonstrated consistent performance at 30 million, just over 30 million transactions per second. And these are transactions that basically simulate a banking commerce. You have a warehouse with stuff, and if you sell the stuff, this goes down and that goes up, and the money goes this way and that way. Complicated reading, writing, updating, all of these transactions, and they can do 30 million per minute. Which, what is this per second? Something very large. I looked at the QuantCast ratings for different websites. This is about how many, 30 million is about how many hits StackOverflow.com gets per, I think it was an hour or day. I think it was day. So imagine how many queries you would have to have per website load in order to reach this limit. It's really not there. And this is before you do any caching whatsoever. The possibilities are endless. Basically, I'm trying to prove to you that it's fast enough for Chirper, our Twitter clone.
But expensive.
But expensive, to be fair. This 1700 cores is, I don't have that. But for the longest time, this is kind of the fundamental thing. The question was, how do we store data? What tool do we use to store data? That was answered. We're definitely using a relational database. The question was how to make that relational database faster. People focused on this for years and years and years. Then Amazon happened. Amazon was a bookstore. That was their first business. Now they are a cloud computing platform. This is kind of how they made that step. Amazon, in 2005, started building Amazon Dynamodb. They finished it and released a paper about it in 2007. How many people have heard of this? Okay, almost the same number as the cap theorem guys, which doesn't surprise me. The fundamental thing that they started out the paper with is that for all of what they do, almost everything that they do, except for data analysis, which they can do later, they do not need relational databases. We've spent 30 years trying to make sure that whatever complicated, ridiculous joining, mixing group by query you can make that it will work and it will work really fast. And Amazon said, actually, we don't need any of that. Most of what they do can be accomplished by a single primary key value store. So they built one. And they built it exclusively on primary keys. There were no transactions. And there were some relaxing things that they did here. X equals 7 would say one computer, X equals 5 on another one. A relational database will make a choice. One of them succeeds, one of them fails, one came after the other. In Amazon's database, it's totally possible that if you ask the system what is the value of X, you will get 2 answers, 5 and 7. Good luck. They didn't do consistency in the database. They intentionally avoided it. They didn't want to deal with it. They didn't want to do transactions. They took nothing, almost, from the last 30 years of relational database research and applied it to their new thing, which runs one of the largest stores online, pretty much, period. And they did this because they found that they didn't actually need it. Rather, not so much that they didn't need it, but that they could live without it, because the alternative to consistency is you can push availability a lot further. What does availability mean? Availability means that if you ask the database something, you will get an answer. The more often you get an answer, the better your availability is. Relational databases will sometimes tell you, I'm sorry, I can't tell you right now because things are going bad. The hard disks have crashed and the replicas are down. Especially for writes, this is a problem. I cannot write this right now because if I write it, I don't know where it's going to go because the machines are crashed. It's kind of this very cautious, hopeless system. And it turns out, this is what they draw it in their paper, Amazon is very happy to fix the problems caused by inconsistency in their database. The example that they give is a shopping cart. The Amazon shopping cart works such that if you add a bunch of things, say you're buying programming books, you add 10 programming books to the list and you realize, wow, that's really expensive. Maybe I don't need these 3, and you delete them one by one by one. What may happen is, and you won't notice it because you're not going to read the list more than a couple of times, as you go through paying, there is some failure in the network somewhere, and one of those books, or all of them, comes back. And you actually pay too much, and you get 10 books instead of the 7 you wanted. Amazon finds that it is cheaper for you to call them, and they will fix your problem. They will give you the money back, they will pay for the shipping to return the book, they will bend over backwards to make you happy, and that is better than them telling you you can't buy anything right now because our database is having trouble. This is the bombshell idea. And why did they feel that this was okay? So when you do this, you're clearly gaining something that you can always be available. And that's already, you can kind of do this with a caching system. I guess you could think of ways around this. But even further, the things that really made it hard to do this with the relational database is they wanted this property of masterless replication. Let's go back to that slide I had before with the master-slave. What I say here, you do this as long as your writes are relatively few and you can do as many reads as you want, you can have as many slaves as you want, that part's easy, right? As soon as you have too many writes to do, you need to do this multiple times. And all the customers whose name starts with A are in this shard, the B customers are in this shard. It becomes a lot of machines, and you have to pay a sysadmin to make sure that every one of these little clusters has enough machines. For Amazon, this was a big problem, or at least it was a big cost. And they wanted to get rid of this. And when you eliminate all of these things that you were trying to do to make things consistent, it turns out that you get this feature of masterless replication. Peer-to-peer has known how to do this for a while. Nutella, Skype, all of these things. They work in this way where they heal themselves. If faults happen, you don't have to go running around. You can always write to them because anyone will accept your writes. And the cost of that for Amazon, this is the trade-off that they made, is consistency. If everyone can accept your writes and say, yep, got the information, then you're going to have 2 values for X eventually. And their bet is that this will happen little enough that it won't be a problem. And get a little bit more into the technical stuff. The secret sauce to this is this read repair. Most of the time, the case that I described, where you deleted 3 items out of your shopping cart and then they reappeared later, this is kind of like when things go really, really bad. Most of the time, it's not that bad, actually. You have these kind of temporary network flaps where half the database thinks you deleted those books, the other half doesn't know it yet. because the internet is slow, or something is temporarily blocking it, but eventually it will get there. And actually, you didn't do anything that's very hard to understand. You had 10 items, and then you had 7. There's a clear temporal ordering. And what they find is that for most of the cases, and they do great analysis on how often this happens for them, when you find those 2 items, you actually, if you added extra information when you wrote them, you can resolve it. And the system down the line will actually understand that you meant to buy 7 books. You don't even have to get to the point where you receive the 10 and get the bill for the 10 and have to call them. Very, very clever stuff. There's this, everyone who gets very excited about this cites this one particular theorem. I asked before, who knows the CAP theorem? And I've mentioned these terms, consistency, availability. This is kind of the root of it. CAP theorem was in 2000. It was by Eric Brewer, who's a prolific researcher in distributed systems. He said that you have to pick 2 of the 3 things. Either your system will be okay if a machine disappears from the network, or even worse, if the machine goes off and does its own thing, independently of the rest of the network. That's tolerance to network partition, that's the P. Or consistency, all of the data is exactly what you think it is all the time, and everyone agrees what that data is, so there can't be 2 values for X. Or availability, which we've talked about. It always has to give an answer. And by the way, 500, the B's there in my eyes, is not sufficient for availability. That doesn't count. It has to give a real answer, that what value it thinks is in the system at the time. It's actually, what he wanted to push is this spectrum between acid and base. Acid you guys may have heard of as well. This is pretty much the relational database thing. Everything is atomic, consistent, isolated, and durable. You never lose information, and it always makes sense with everything else. The alternative, he said to that, and he phrased this as an alternative, and this is why it all went bad, is this basically available soft state, eventually consistent system. And everyone was like, I don't want that. That sounds complicated. So this kind of failed, and this worked better, because people do well with pick 2 of 3. This is a problem that's come out multiple times. It kind of almost worked, too. He gave this particular acid-base thing in several more presentations over the years following the CAP theorem. It still shows up occasionally. But basically, people took the acid-base categories and plugged in SQL versus Dynamo in here. And this is what happened when Amazon came out. Everybody went nuts. Everything had to be this basically available soft, eventually consistent system. And everyone started building things where there were absolutely no SQL databases allowed. The people that wanted to do the databases, because they're good and fast and we know what to do with them, they were the old fogies. We need to get by this. And this is the worst thing. This eventually consistent thing, actually the lack of consistency in general, is not new. SQL databases have been doing this forever. Oracle, MySQL, and Postgres all have these 4 different levels of consistency. One of them means that there is no consistency. You can actually turn it off and it will stop doing work for you. You're welcome. The other one is that you may read, and some of your clients will read old information, and others will read new. There's another one where sometimes you'll have these phantom writes that appear in the wrong order, but eventually it works out properly. This whole idea that consistency exists is a lie. Because actually, not only do they offer those 4 things, pretty much 0% of the world actually uses the serializable, maximum consistency, everything makes sense all the time thing. So it's amazing that nobody notices this, actually, because you get so close to consistent without actually having the database set to that setting. Be consistent, please. So Amazon got rid of it. And this, as I said, everyone went nuts. We had Riak come out after that, and this is, if you ever see a Riak talk, they're really brilliant. These guys are leading the way on cloud storage and cloud data structures. Every cache system could now be like, oh yeah, we've been doing that for a while too. Cache systems tend to be eventually consistent, or just inconsistent, depending. Cassandra, you guys may have heard of. Project Voldemort was a little bit more under the waves. This all has happened in the last 6, 7, 8 years. And it's so good. Don't need to worry about those transactions. You save a bunch of CPU. You don't need to parse SQL. You don't need to do SQL. You don't need to do any of this hard stuff, especially not sharding. You also can't query your data, but that's what we have Hadoop for. And Google was having none of it. Google did not follow this trend. They had MapReduce, which was a solution for a huge amount of data, but they never gave up on consistency. And eventually they snapped. They had it. They released their own paper, which introduced the spanner database, aka the Stop Being Lazy database, how I remember it. And they made a couple of points, and I think these points are salient. First off, you don't have this problem. We built our own Twitter in the first couple slides. It doesn't have this problem because nobody uses it. Even if, let's say, let's go nuts, everyone in Tallinn starts using our new Twitter, it's going to be like 20 transactions per second maximum. And that's if we do it with transactions, which would be dumb. If you are this big, this is point 2, you are big enough to buy your own atomic clock. Turns out atomic clocks aren't very expensive. It's like a couple $1,000s, less than 10. You can install them, and magically all of your data center's computers have almost exactly the same time. I drew these beautiful graphs, actually, to show how close you can get to exactly synchronized time, which is otherwise this inescapable ideal. NTP, if anyone's thinking that, doesn't work. It doesn't work. You will drift seconds at a time and then correct, and drift seconds at a time and correct. It's not good enough for this. Point 3 is probably the most salient, which is that this is where they accuse Amazon of being lazy. We are engineers, they say. Just because consistency is hard doesn't mean it's possible. Apply your brain, fix the problem, make it work at the scale that you need it. And so they did. They proved that they have the biggest, brainiest skulls on the planet, and they did it better than all of the rest of us. I included a couple of graphs here to show. They had, for multi-data center commits, they had 100 millisecond latencies while doing these transactions, which are perfectly serializable. And they showed that if you buy your own atomic clock, you can get synchronization among computers within a data center within a millisecond, 99% of the time. 99.9% of the time, it's less than 6 milliseconds. That's pretty good. And they do it. And this actually powers Google's advertising backend. So all of those guys that were doing their eventually consistent thing, thinking this is the future, this is web scale, Google is saying that we're wrong. And it's a little worse because people started building things on these eventually consistent systems. Amazon obviously had done it before. They had their shopping cart and they started building other things on top of it. The rest of the world also went down this path. And it turns out when you turn off consistency, this one thing that before you never had to worry about comes up. And the way that Eric Brewer, the guy that proposed the Kappa theorem originally, codified it, is that the invariance of your system, the things that have to be true for the results to not be insane. If things are in consistent systems, they tend to not be that important. You actually don't have to know what they are. You can kind of store your data, it'll be there, sure. And you can query it, it'll be there later, and you can buy things and sell things. But you don't actually have to be constantly aware of them while you're programming the application. When you start doing eventual consistency, all of these things come out of the woodwork. You have to solve for every single important race condition that's ever going to happen in your code. And you have to solve it for the case where you're going across 2 continents to do it, if you've achieved the kind of scale where you're actually balancing across 2 continents. So this is kind of true. And as a consolation prize, SQL databases actually are not that bad. And the part about maintaining the machines yourself, you can now pay someone to do that for you, which is nice. This is depressing, right? We'd spent 7 or 8 years working on this, and it's all been for nothing. That is what Google says. I prefer to think of this in a little bit of a more positive light, and this is kind of the conclusion that I'm hoping to draw you to through this talk. Cloud storage, and in general the cloud, the decision to move to the cloud at all, the decision to use one database system versus another, it's all about trade-offs. I talked earlier about this masterless right anywhere replication, right? You have to, when you build a system, think about what does it cost to just hire someone to watch the machines and wake up in the middle of the night when anything goes wrong, when the power supply fries out. Do I really have to worry about this? Is it so expensive to keep track of these things that we can't just do it? If something does go wrong, how bad is it? That's another thing. You really have to think, and particularly if you're considering using Riak or Dynamodb or one of these, you really have to think about how long it is going to take you to figure out your system's invariance. This is where it's, I have no evidence of this, but it feels to me, the little I played without it, as an exponential scale of how complex your program is and how hard you have to work to make it work on an eventually consistent system. But maybe you're on the low end. Or maybe the things that go wrong are actually not so bad if they do. And your customers will actually be okay with this. This is possible. Another trade-off. Relational queries. We kind of forgot them while we were doing Dynamodb and all of these things. And some of the other ones that comes out, the one that drives me nuts in particular is Azure Tables, don't have a way to grab huge swaths of data, MapReduce style, and store them into another thing. It's actually kind of an expensive thing to do such things like that. So you have to ask, how important is it to be able to look at the complete set of data and run these business analytics queries on them? Can you store it in SQL and put one of these eventually consistent cache-like things on top of it? Maybe that's a better system because then you still have your data in some form in a consistent fashion. Can you load it in there later? Can you use flat files? This is kind of the Google MapReduce answer. It's too hard to, it used to be anyway, too hard to do this for the amount of data they had for Google Maps, so they just used files and algorithms that knew how to deal with files. The situation really isn't hopeless. We're not going back to relational databases 100%. The CAP theorem, Dynamo, and all of this is about trade-offs, and particularly with the cloud and our increasing accessibility to all of these technologies. This is kind of what we have to think about. So, this is my last slide. Do you guys have any questions?
Is Amazon doing relational database now, or what are they doing? Are they still using Dynamo?
They are.
Okay.
In fact, so Dynamo is so popular within Amazon that they started selling it without Amazon. They started selling simple versions of it, SimpleDB. Now they sell Dynamo in its raw form. It continues to be useful for them. I think they really benefit from the lack of having to hire sysadmins to manage master-slave replication. They definitely still use it.
Do you know about the background of the initial decision? And actually, it looks like a business decision that we drop the consistency and actually allow for, I don't know, customers to call us and require money back or something. This looks like it was like a business decision to go for eventual consistency.
Yeah, if you guys find the Dynamo paper, it's very easy to Google and find. Werner Vogels is a really great blogger about distributed systems in general, and it's easy to find this paper off of his website. They go into exactly the constraints that they had. They have service level agreements you've probably now heard of. This is one of the new buzzwords. They had a system where they already knew what promises they had to make, and they had realized that thing I mentioned earlier where it's more expensive to deny customers that you cannot buy something now because something's broken than it is to fix their problems later for them. Especially when you think of the thing like books from Amazon. If I get 10 books instead of 7, I really have to think, is it worth my time to call them and put the book in a box and go to the post office and deal with this problem? Or did I just get, not so much free books? So it is exactly motivated by these business decisions that they have.
That's right, but I think at least what general public knows that there is a Postgre. So is there anything else for like less consistent, or is Postgre not consistent?
Yes. I mentioned that we're using Azure Tables in particular. Yeah, a couple of things already work using Azure Tables and this storage. I don't think we've hit that one application that's really central to our business. And there's some things that we're going to try some other things before we move Skype out, the calling to PSTN telephones, because that makes all of our money. So maybe we'll wait to do the experiment later. Azure is very new, and one of I'm going to call it a constraint, but really it's a larger business decision. It's good for Microsoft if we use Azure as opposed to Amazon. So unless we prove that it's not sufficient, when we move to the cloud, we move to Azure. And what we found is that we can do it. All of these things that I mentioned about it's a lot of work to move to these kind of key value storage things with limited querying abilities, it is a ton of work. All of the little edge cases that come up, and this is probably going to change our designs going forward.
Azure uses has also its own key value store?
Yes, they do. It's called Azure Tables. They go a little bit different of a different way. They do not I mentioned React before. React is a perfectly, like, they read the paper, every word of it, every line of it, they thought about it, they meditated, and they produced React. And it's exactly the same thing, except it's open source. Microsoft went and they said, this consistency thing, we think you've gone too far. Key value stores are great, because then you don't need to do so much query processing and planning and all of those hard things. But they prefer a consistent model. And there's actually work that came out in, I'm going to get the date wrong, I think it was 2009, that criticized Amazon's assertion that it's so hard to provide consistency at the key level value. And Microsoft actually employs that paper, so they actually have some degree of consistency per row. At least snapshot isolation. They will always give you one answer to the question, as opposed to two.
I think what you're missing that you're confusing Dynamo and Dynamodb, because Dynamodb could be run as strongly consistent. It's by default.
Oh yeah. I think Dynamo and DynamoDB are still the same thing.
No.
But we're
Dynamo
talking.
was like the paper. DynamoDB is the product, which was on.
Which uses the thing that was built in the paper. I think. Anyway.
But you could
So-
assume the consistent.
This is true, actually. This is one interesting thing. They recognize that not all applications are okay for this very inconsistent model, so they made it tunable. And I didn't want to make this a Dynamo talk, so I didn't get into this. But you can tune up to the point where you have to be perfectly consistent on every write. And you can do this per request. Some writes are perfectly consistent, some writes aren't. And there's the concept of a sloppy quorum that they use to make these decisions. I'm surprised so few of you had heard of the CAP theorem. When I read it up front here, did it seem more familiar? Or was it still new? Yeah. Okay, this has been heard. That's good.
What is the market for atomic clocks in the nearest future?
I don't know. Demand has gone up. I'm not sure if supply has gone up.
Should we see some atomic clocks
Yeah, so
much everywhere?
I was thinking about giving this talk as like, how do you order things in a distributed system? And the kind of, the question you have to constantly ask yourself is, if I have to return things in a certain order, like the order that they happen, is it not sufficient to just write the row with a timestamp at the end of it and run with that? It depends. And it really depends on the frequency at which you're writing to this thing. If the frequency at which you're writing is much less than the frequency of your clock synchronization, like you don't think the machines will be more than 60 seconds apart from one another, then timestamps will probably be okay. Until the one day when something happens and then they think, is that really so bad? And maybe it is, maybe it isn't. The reason Google bought this atomic clock is to make that window really, really small. So actually what they do is they do locking on the back end, and they do this kind of delayed read thing. They delay the visibility of every read until you're outside of this window that the atomic clock gives you. So that 6 milliseconds that they had, that's how long Google has to wait to make their writes available to readers. Most of us don't write things that happen at the millisecond granularity.
Who knows what happens with big data soon?
Yes. Yeah. And this is Google's point one, is you're not this big.
So, one question, how do you decide when do you use atomic clock versus vector clocks? Because vector clocks allow you to solve this problem without any synchronization.
They don't allow you to solve the problem all the time, actually.
Yeah.
Who knows here what vector clocks are?
Is this the
That's
stuff
good.
that Clark times doing?
Sorry?
Is this the stuff that Clark times doing?
No.
No? Okay, I'll give it, okay. Vector clock is such. Let's say there's...
I had a picture on the side.
Yeah, but it's kind of an ugly picture. I'm going to make a better picture. All right, you have 3 people in the system that are doing things, right? And at any given point in time, you're going to have a vector that looks like guy A did 3 things. Guy B did 4 things. And C has done nothing yet. What vector clocks will help you do is they'll help you make certain assertions. For instance, if you take this clock, which is x equals 5, this is what I'm talking about when you add extra information to your writes to make them clean upable later. So if you have x equals 5, has the vector clock this, right? And then you have a different operation, x equals 7, and that was done by C. What you do is you increase C's counter here. B is still 4, because he didn't do anything. A is 3 still. What you can do, and this is very fast to do, and there's a couple of algorithm papers to make this even faster. I can't imagine why. If you look at two clocks, and one of them, for each of these values, is greater than the other. So 4 is greater than or equal to 4, 3 is greater than or equal to 3, 1 is greater than 0. Then you know that there's this causal ordering. So this solves some of the problems. And this is kind of what I was alluding to, that actually the case where you get 10 books instead of 7 doesn't happen very often because a lot of them look like this. Now, on the other hand, what if you get, let's say we got to x equals 7, then we say x equals 13 because it's unlucky. And we have now A3, B5, C1. So B wrote this one, right? And at the same time, someone else says x equals 0, and that was A. So now you have A4, B4, C1. Which of these happened after the other? By looking at the instances in the logical timers within it, A did something after this, but B did something after this. So there's this kind of like circular relationship between these two things. Vector clocks don't always solve your conflicts. What they do is they make the conflicts visible, so that the system knows when it actually has one answer and the system is just being inconsistent, and it can give you one answer, versus when there's actually two possibilities. And at this point, this is where it gets complicated for the developer, because you can't just store things. You always also have to be ready for multiple answers to come up. If I bought books 1 and 2 in this shopping cart, and something happened, and it's books 2 and 3 in that one, what Amazon will do is it will just give you 3 books. They just take the union of all the things in the set that's marked with these vector clocks, and they'll make it happen this way.
Also business decision. Sell more.
Say it again?
Also business decision.
Yes.
Sell more.
Because probably they're not going to take the time to call them and give the book back. Maybe they will, in which case they'll happily bend over backwards to make the disgruntled customer happy. So yeah, this is vector clocks are not a solution to the problem. They are a tool for exposing the problem, if you want to have inconsistency at all. Cool. So the projector is off. Thanks.
Thank you.